4.3 Derivatives and the shape of curves. The mean value theorem is a big one for us, and it says that if f is a differentiable function on the interval a to b, then there exists a number c between a and b such that f prime of c equals f of b minus f of a all over b minus a. In other words, so that the instantaneous rate of change is equal to the average rate of change somewhere. The slope of the tangent line equals the secant line somewhere. Here we see a great illustration. At some point along the graph, we see that the slope between 2 points is equal to the tangent line at some point within the interval. This can happen more than once. If you just multiply things out, cross multiply here, you would get f of b minus f of a equals f prime of c times b minus a, and you'll realize that this is just y2 minus y1 equals the slope times x2 minus x1. Here we're saying that if an object moves in a straight line with position function s equals f of t, then the average velocity between time equals a and time equals b is just f of b minus f of a all over b minus a, and the velocity at t equals c, the instantaneous velocity there, is f prime of c. The mean value theorem is going to say that at some time t equals c between a and b, the instantaneous velocity f prime of c is equal to the average velocity. The best way that I can explain this to you is what this says right here. And this is the mean value theorem. It says, for example, if a car travels 180 kilometers in 2 hours, then the speedometer must have read 90 kilometers per hour at least once. In other words, the average velocity equals the instantaneous velocity somewhere. I'm also going to have you watch a fun little video, and it really sums up the mean value theorem very nicely. Basically, it is this little video where a police officer pulls somebody over and says, well, in the last 2 hours, I saw that you went 120 miles. So the police officer says, in the last 2 hours, you traveled 120 miles. The speed limit was 45 miles per hour. Therefore, you get a ticket by the mean value theorem. And so why does that work? It's because the average velocity he was traveling was 60 miles per hour, right? And so if his average velocity was 60 miles per hour, then I know that at least once during his trip he must have been traveling at 60 miles per hour, and so he would get a ticket. An increasing function is just saying that the derivative is positive on that interval. A decreasing function would mean that the derivative is negative on that interval. So if we look here, we can see that the derivative is negative from here to here and that's where the function is decreasing. So don't get confused. The function increasing means that the derivative is positive. The function decreasing means that the derivative is negative. So let's go ahead and find where this function is increasing and decreasing. So we need to know something about the derivative. Let's go ahead and find it. We can factor a 12x out. And so, let's go ahead and make our sign chart for the derivative. Our zeros are at 0, at 2, and at -1. If I put in a number like -2, I would get a negative times a negative times a negative, which is a negative. If I put in a number like -1/2, I would get a negative times a negative times a positive. If I put in a number like 1, I would get positive times a negative times a positive. And then a big number, I get a positive out. So we know it's increasing is where the derivative is positive, and that is on this interval and this interval. And it's decreasing where the derivative is negative, and that would be on this interval and on this interval. The first derivative test is crucial, and you guys have all kind of caught on to this already. The critical points that we learned about in the last section, we saw when we talked about it in class that at the critical point, we might have a maximum, we might have a minimum, or we might have neither. Recall the y equals x cubed case? So in order to actually see if we have a max or a min, we want to look if the derivative changes sign. Because if the derivative changes sign, we know we have a max or a min. Now let's look at a picture. If the derivative changes from positive to negative, then we see that we have a maximum. So we see that right here. From positive to negative, we have a max. And I like to write it like this. The derivative goes from positive to negative. That has a positive slope, that has a negative slope, and that's clearly a max. If the derivative was negative and then it goes positive, we have a min, which is figure B. If we go from positive, 0, positive, so we have no change in sign, then we have no max or min. Similarly, negative, 0, negative, we have no max or min. So what we learn here, the main takeaway, is that we only have a max or a min if the derivative actually changes sign from positive to negative or negative to positive. Concavity, and we'll see a picture on the next slide. We know that it's concave upward if the rate of change is positive. In other words, if f double prime is positive. Remember, f double prime positive means what? It means that the derivative is increasing. Remember, whenever you have a function increasing, it means that its derivative is positive. So here, I kind of went backwards. I said, if the second derivative is positive, then the derivative must be increasing. I went backwards from what I had here. Concave down means that the rate of change is negative. And so let's look at this graphically to really understand what we're saying. Concave upward is happening right here. Concave up is a happy function. Concave down is not so happy. This is concave down, this is concave up. Concave up where I'm red. Happy faces. Right here, it's concave down. So what I'm saying is that the rate of change is increasing. My slope is continually getting larger and larger and larger on this first red region. Even though my derivative started negative, it's getting larger and larger and larger as time goes on. Here, I suddenly see from here to this point here, my derivative got less steep. And so at this point P, because I'm changing from my derivative getting more and more positive to it starting to get less positive, I see that I went from concave up to concave down. This point right here where I change concavity is called an inflection point. A point where a curve changes its direction of concavity is an inflection point. In other words, it goes from concave up to concave down or concave down to concave up. The concavity test just recaps what I said previously. In order to determine a local max or min, you have two ways. The first way is to use the first derivative test. And make a sign chart. And that's really my preferred method. But another way is to look at the second derivative. So if you know that the first derivative is 0, you know it's a potential max or min. It's a critical value. And if you also know that the second derivative is positive, then you would know that it is a local minimum. Because remember, this is saying it's concave up. So if you know the derivative is 0 and it's concave up, then it's a local min. Similarly, if the derivative is 0 and it's concave down, then I have a local max. I tend to prefer this method, and you'll see me using that a lot. So let's go ahead and discuss the concavity of this function first. So the concavity is going to be looking at the second derivative. And so I'm just going to factor that. And so then I'm going to make a sign chart for my second derivative so I can discuss the concavity. I see my zeros are at 12x equals 0, 0, or 2. And so if I put in a negative, I get a negative times a negative. If I put in a 1, for instance, I would get a positive times a negative, and then I get a positive. So I know that it's concave up, where the second derivative is positive, and that would be from negative infinity to 0, and from 2 to infinity, it's concave down, where my second derivative is negative, in other words, from 0 to 2. In order to find my inflection points, well, that's just where I changed from concave up to concave down, and that happened at 0 and at 2. If I want to find my actual points, then my point would be 0. I plug in 0 and I get out a 0. 2, I plug in a 2 and I get 2 to the 4th power minus 4 times 2 to the 3rd power, negative 16. Where do I have my local maximum and minimum? That I have to look at my first derivative. So I have my first derivative here. I'm just going to factor out a 4x squared. And so if I make a sign chart of that, I have a 0 at 0 and at 3. And so if I put in a negative number, I would get a positive times a negative. If I put in a 1, I would get a positive times a negative. And if I put in a large number, I would get a positive times a positive. So all I see going on here is that I change from negative to positive meaning a min. You see, because I was negative slope, so I drew a negative slope, then a positive slope. And so we have a minimum at 3, and f of 3 equals negative 27. That would be a local min. I have no local max. And so if we look at a picture, we can clearly see here are my inflection points because I'm changing from being happy at this moment. My function changes. It starts slowing down its derivative. And then here I become happy again all the rest of the way. So those are my concave up regions. And my inflection points are separating concave up from concave down regions, and I only have one local minimum. So let's do this one more time. Let's first discuss the concavity. In order to take the derivative, I want to see if I can simplify my function, and I just can't in this case, so I've just got to work with it. Take the first derivative, and I need a product rule. So the derivative of the first times the second plus the first times the derivative of the second. And when I want to take the derivative of this, I have a baby. The derivative of the baby is negative 1. And so I am going to go ahead and try and simplify this right now because I'm going to need to find the local min and the local max in the future, so I may as well simplify it right now. So all I did was I put all the positive exponent stuff in the top and all the negative exponent stuff in the denominator. And I'm going to just go ahead and get a common denominator at this point. So I see that my common denominator, I need the 3. It's in both of them. I need an x to the 1/3. And then I need this guy. So to get from this denominator to this one, I multiply it by 6 minus x to the 2/3. So I'm going to do the same thing on the top. To get from this denominator to this one, I multiply by an x to the 1/3. So I'm going to do the same thing on the top. this simplifies my life greatly because I see that I have something to the 1/3 times something to the 2/3. So you add the exponents since I have the same base. So I just have 2 times 6 minus x. And then x to the 2/3 times x to the 1/3 is just x. So I have 12 minus 3x. Let's take a 3 out of the top, and I'm going to divide it with the bottom at the same time. So I'm left with 4 minus x over x to the 1/3 times 6 minus x to the 2/3. That was pretty difficult. You know what? I'm just going to tell you what the second derivative is. If you want to play with it, you can, but it's not even worth it. This problem's getting too messy. So go ahead and take it from me. That is the second derivative. Now let's finish our problem. In order to find concavity, we have to find where our second derivative is positive and negative. So let's go ahead and make a sign chart. Where does the second derivative equal 0? Never. But remember, not only where does it equal 0, also where is f prime prime undefined? F prime prime is undefined when x to the 4/3 equals 0. In other words, when x equals 0, or when 6 minus x equals 0. In other words, when x equals 6. So at 0 and at 6, I'm going to put open circles here just to remind myself that it's undefined at those points. So now I'm going to do the same deal and make my chart. I'm going to go back here. I know the numerator is always negative, and so when I check my denominator, I get a negative. So that would be, let's put in a -1, I would get a positive, and then I would get a positive. So a negative divided by a positive is a negative. If I put in a number like 1, I would get a positive times a positive, but on my top I would get a negative. So a negative divided by a positive is a negative. And when I put in a large number, I would get, from here, I would get a negative on the bottom, and a negative divided by a negative is a positive. So I know that it's concave down from -infinity to 0 and from 0 to 6. And so that's the importance of my open circle, so that I don't just say from -infinity to 6. Do you see that? That's really crucial. It's concave up from 6 to infinity. At this point right here, I would rewind the lecture and listen to me say this part all over again, because this was difficult. You need to be able to make the sign chart. You need to understand the importance of these open circles, because that's where the second derivative is undefined. You need to understand why, if you didn't remember the open circles, you would have gotten the wrong answer right there. Now moving on, where do we have our point of inflection? Remember, that is just where we're changing from concave up to concave down, or concave down to concave up, and that only happens at x equals 6. The point it happened at would be 6. If we put in a 6, we get 0. And in order to find the local min and local max, we need to make our number line for f prime. And so we already worked out f prime over here, and we see that f prime equals 0 when x is 4. So at 4, we're going to have a closed circle because that is where the derivative actually equals 0. And then, where is f prime undefined? When the denominator equals 0. When x equals 0, or when 6 minus x equals 0. So, at 6 and at 0, I have open circles. Now, just stick in some numbers and you should get negative, positive, negative, negative, meaning that we have negative to positive is a min, positive to negative is a max, and so we have a local min, negative to positive, that's happening right here. And then from positive to negative is a max. That's happening f of 4. And so that is our answer. Let's just go ahead and look at the graph. And so you'll see that this is why f prime was undefined. But even so, it's a local min. You'll see that at 6, this was another place that f prime was undefined. And it happened to be neither a min or a max. And we saw from our sign chart that f prime went from negative to negative. Here was the other point where f prime was actually equal to 0, and we saw that f prime changed from positive to negative. So this is a lot to understand. Go back and make sure that it's all coming together for you.